Okay, folks, thank you for coming along to see what I think is the presentation with the longest title in the entire conference. Might be some tight competition with a Friday morning talk, but I'm going to stick to my guns there. There's a large number of co-authors that are mentioned under there. Primarily, these are people associated with an USU workshop on the subject of solar wind effects on the electrodynamics of Mars that took place last year. What I'm going to tell you about today is all that stuff up there. This is primarily a show and tell presentation rather than anything where we have completed the entire analysis and have tremendously insightful results to share. So there have been a goodly number of studies performed looking at the solar wind throughout the heliosphere. There's been a goodly number of studies looking at magnetospheres throughout the solar system, including the Mars magnetosphere, which you see featured in this example from Yingzhuan Mars numerical simulations there. There have even been studies performed of ionospheres throughout the solar system, including the Mars ionosphere. And you see that the topside ionosphere can really change significantly from observation to observation. One possible mechanism for making these changes will be changes in the solar conditions forcing on the top of the ionosphere. And that's kind of the direction that we're going to go in today. Now, the underlying motivation for this study was that there are lots of studies that looked at sort of what one interface between a pair of these regions there, but there wasn't much out there that looked at stuff coming in the solar wind. What does it do to the magnetosphere? What happens when it gets the ionosphere close to the planet? So that's what we're trying to do today. And I'm going to be using data from the Mars Express spacecraft primarily. Unlike the luxurious terrestrial situation where there are fleets of spacecraft upstream of the magnetosphere, in the magnetosphere, lots of ground-based observing stations in a global network. Out at the other planets, we're bootstrapping our way with a single spacecraft. The time frame we're interested in, March, April 2010, because there was some fortuitous geometrical alignments at that time. We have the Sun up there, stereo A and B highlighted there, Earth at 1 AU from the Sun, and Mars down in the lower left corner there, on about the same arm of the Parker spiral as Earth is, also facing roughly the same hemisphere of the Sun as Earth is. If you were ever to attempt to extrapolate solar wind conditions from Earth out to Mars, this is about the best kind of scenario for accomplishing that. That's not to say it's a perfect thing to do, but it's as good as we are going to get. Now, the rest of my talk is going to be showing you observations from those three regions: solar wind, magnetosphere, ionosphere. We've got lots of solar wind data, we've got lots of magnetospheric data. Where we're limited is in the ionospheric observations. Primary mode for looking at the ionosphere consists of radio occultation observations, which have a lot of nasty geometrical and other requirements on them. So we've essentially only got 14 radio occultation measurements made during this time period there. And I've highlighted on this lat-long grid of Mars where these 14 occultations are. And the background in this wonderfully colored picture, I'm very proud of the color scheme there. The background on this is the magnetic field strength in the ionosphere of Mars, just indicating how non-terrestrial this environment is. This is not a global scale dipolar magnetic field at all. Having said we only have 14 radio occultation observations, I'm going to strip that down a bit more and focus just on 2 of them. That's the pair in that circle there that come from 2 days apart, basically the same latitude, same longitude. Motivation there is if there are changes in the ionosphere from one observation to the next, we can somewhat confidently attribute those to temporal variations in the forcings that drive the ionosphere. And I'm going to reference these two orbit numbers, 8051, 8058, a lot as I go through things. On to the solar wind next, and then moving inwards from there. This is a complicated plot. It's got a lot of stuff on it. Let me focus you on the essential stuff. Time runs on the horizontal axis there. I've got the two orbits highlighted there. 3 panels with red and black measurements are solar wind conditions. We have solar wind speed, a few hundred kilometers per second, solar wind number density, few particles per centimeter cubed, and solar wind dynamic pressure, just less than a nanopascal, say. The black points in these 3 panels there come from extrapolations of wind observations at Earth. So we can have a continuous time series of them, but we're a little hesitant as to how accurate they are. The red points that you see sporadically appearing there are inferences derived from ASPRA charged particle observations on the Mars Express spacecraft. ASPRA is not designed to characterize the solar wind at all, so there are some challenges associated with interpreting the measurements that way, which is why the error bars sometimes start to stick up a bit there. Let's see what the conditions are in the solar wind for these 2 orbits. So 8058 first, solar wind speed matches in the extrapolations from Earth and what's actually observed at Mars. So good things there. On the earlier orbit, 8051, the observed speed is a lot slower than the black extrapolated speed. That means that our black slug of very high density solar wind there, we predict to arrive shortly before orbit 8051, is actually going to hit bang on orbit 8051 when we have these ionospheric observations. That's that red data point there. 8058, quieter, more quiescent solar wind conditions there. If the scale on this dynamic pressure plot was not being dragged off by this event there, you would see similar kinds of things there. High dynamic pressure on 8051, lower dynamic pressure 8058. This is going to impact the magnetosphere. And have a few energy spectra from the ASPRA instrument here. The 4 panels are proton data and then electron data. We have an energy axis that I can't read and a time axis that spans about 3/4 of an orbit there. And the periapsis on this elliptical orbit is in the center of things there. If we focus on the proton data for a moment, just comparing those 2 orbits. We have a more compressed magnetosphere on the first orbit there. These boundaries are closer to the center than they are in 8058. We also have higher densities of particles in the magnetosheath on 8051 than 8058. That's those reds and oranges there, which are conspicuous by their absence around there. So looks like the magnetosphere is responding to that solar wind event coming through on the first orbit. Now for the ionosphere, we've got electron density as a function of altitude there from the first orbit and the second orbit. The blue data points that you can't see on the plot are the raw, unsmoothed measurements. Smooth them a little bit to make the story easier to tell. Those are the red points there. And if you flick your eye back and forth between the 2 profiles there, you see that there are larger topside densities on the second orbit than on the first orbit. If you track this 10 to the 3 electrons per cubic centimeter line there, you see you're getting high plasma densities at 450, 550 kilometers altitude, whereas on this orbit, no appreciable amounts of plasma at those altitudes. It's a little bit easier to see if I plot those two orbits back to back. You see 8058 in the red points has higher densities in the top side than 8051 in the blue points. There's no change down in the main regions of the ionosphere, indicating that solar wind effects only propagate so far. So the story we have to tell from this case study of those different regions is that our first orbit is characterized by compression. High dynamic pressure in the solar wind squishes the magnetosphere, enhances magnetosheath densities a bit, and reduces the plasma densities in the topside ionosphere. On the other orbit, conditions are more relaxed. And that's all I have. Thank you.
Thank you for a nice talk and comments or questions. Let's get some microphones over there. Ingo?
Just a small comment. I thought in the, is it 8058 case, there was a V1 layer, which wasn't there in the other one?
Possibly. I haven't looked.
It shows up there as well.
Let's see.
There?
Yes. So if I had looked at the solar spectra for these days, I would suspect that there is a higher soft X-ray flux on that day causing that feature than there is on that day there.
Okay. Thanks.
And I
That's
think Dan Baker can get the...
Have you tried using WSA-Enlil, to model the solar wind driver as well as your extrapolation method?
No, not yet. But that might be an interesting thing to explore.
I think you can probably get a pretty good profile and check it with the Earth case and have a real nice driver.
Thank you.
On your conclusion table, you showed that when the solar wind pressure is low, there is no ionopause. No, sorry. When the solar wind pressure is high, you have an ionopause, and you don't have an ionopause when the solar wind pressure is low. Now, that's what you found, which, you can't argue with data. But if Mars has any similarities to Venus, to some degree, that's the opposite which was found at Venus.
I didn't have time to squeeze the ionopause plots into these presentations, and I have to say that the Marsis ionopause observations come from a completely different location on the planet from everything else. What struck me was that if you look at, say, this kind of kind of ionosphere that's falling off relatively quickly, you're perhaps more likely to see a sudden transition to low densities in that upper case than in that lower case there. But it's there's no ionopause identified in these radio occultation observations. So yep, in completely different observations from the Marsis topside radar sounder. I knew I should have eliminated that Marsis line from the conclusions.
Okay, let's go on to...
One more point about, at the very beginning when you were talking about the Earth-Mars configuration around the sun, and you said that it was perhaps the best that you could get. I guess maybe it's more of a point with the entire ISI team rather than just you, but you're their rep here, so. I'd say it's much better to be radially aligned in the direction of the solar wind than along a Parker spiral. Parker spiral might be great for SEPs, but not necessarily for bulk solar wind.
Yeah, absolutely. It's relatively close to a radial aligned, but yeah.
Well, no further questions. Thank you.